So what I'd like to do is start with this heat kernel. Heat kernel methods are almost never taught, but I think we're really at the right place to do it. And the homework problem that I started thinking about, which I just handed out, turns out is best solved using it. So let's do it. So first recall that we have the determinant of some operator is e to the trace log of the operator, and trace for us at this stage means integral d4x x matrix element of log of the operator. Okay, diagonal x. Now there could be more traces. So if you're doing something that has fermions in it or has SU2 matrices or whatever, you trace over everything that is there. But since we just have a scalar field now, there's no more traces. It really means sum over diagonal elements of every quantum number. But the trick is that log of the operator is tough to evaluate. We gave you one way to do that last time by this perturbative method. Here's a more powerful way. So we're going to use the following. We're going to use log b over a is the integral from 0 to infinity dx over x e to the minus ax minus e to the minus bx. Okay, so that's just the identity. But then this implies then with our operator that x log O x is minus the integral from 0 to infinity, some d tau over tau, x matrix element e to the minus tau operator, x plus a constant, which we'll just drop. Okay. This is still a nasty, in a way it's a tough beast. Here we've got log O sitting in the exponent. Here we have another exponent in the exponent, but it's easier to deal with exponents than it is to deal with logs of operators. We know there's a nice simple Taylor expansion of this around small o. There's not a great Taylor expansion of that around small o. So just think of it that way. You know, when you're doing low momentum, these operators tend to run like the momentum. The one is much better behaved than the other. And this has been well studied in the math literature. So this heat kernel is the name given to, well, let's give it a symbol, h of x and tau is defined to be this matrix element x e to the minus tau operator x. Okay, so the name heat kernel comes from the fact that this is like, you know, e to the minus beta Hamiltonian that you get in thermo, and you're taking the trace just like you do in thermo. So it also has connections there. The standard reference to cite is in the math literature, Gilkey. And the only book that I know that describes this is us, DDH. And I handed out that little thing there. But the the basic idea is that if you take a simple differential operator, you can work this out once and for all, and that's what Gilkey did. Just look up the answer, and then you've got a general form of the answer here for other things. So let's do an example. If the operator is d mu plus m squared plus sigma of x, okay, with d mu being partial derivative plus gamma mu. Okay, so this compromises an awful lot of things. We'll show how this works in E and M, where gamma is chosen to be minus i.e. gamma mu. The homework problem has you with various forms of sigma of x in there. Okay, but if you just take this form, you can work out what the answer is, and then the answer is h of x in tau is I over 4 pi d over 2. It's in d, this is in d dimensions. Eta minus tau m squared tau d over 2 a0 of x plus a1 of x times tau plus a2 of x times tau squared plus dot dot dot. And the coefficients have been worked out here. For this particular operator, a0 is 1, a1 is minus sigma, a2 is 1/2 sigma squared plus 1/12 d mu commuted with d nu, d mu commuted with d nu, plus 1/6 d mu commuted with sigma. And so some things are known about higher order ones. I actually don't have them on the top of my head, but you'd go to Gilkey to get them up. Okay? But then, once you've done this, x log O, x can be just done. It's minus I over 4 pi d over 2. Sum of n equals to 0 to infinity. M to the d minus 2n gamma n minus d over 2 an of x. Okay. So what you see here is these things to become more convergent at high n. So these things start off typically to be divergent. So for example, the one piece is definitely divergent. That's gamma of minus d over 2. Up to a2 is divergent. So if n is 2 minus d over 2, as you go to the limit, as d goes to 4, diverges. Everything else after that is finite. Okay. So all the renormalization constants, all the stuff that's divergent, all lives in these guys. And okay. Let me just also point out something that's useful for the homework, just since this is probably an odd beast. This goes like m squared plus sigma. I'm going to ask you, forgetting about derivatives of sigma, for higher order terms in this expansion. Okay. In fact, you can do them to all orders, and it's easy to see how you do it. If this if this sigma is a constant, so there's no derivatives involved, then it's m squared plus sigma. It goes like e to the minus tau m squared, and you see that 1 minus sigma plus a half sigma squared. So you can guess then the rest of the series for sigma if you don't need derivatives of sigma. Okay, so that's the clue for the homework. You know this to all orders. It's just the expansion, the exponential. Okay. So it's yeah.
What's the last term of the A2?
This thing. This is it's a double commutator. I need another commutation side. Yeah. It's a double commutator. Let's see. I got it in the wrong place there. Sorry. The second commutator should go there. So you commute d with sigma. So most of the time, you can sort of see. Let's imagine that sigma was phi squared. Then this would be a derivative of phi squared, which would be phi d mu phi, and this would then end up being another derivative. So it would look like two derivatives on phi, on two phis. So okay. So here's an example. Let's do QED with scalars that we're doing. So then d mu for a scalar is d mu plus I e a mu. Sigma in this case is 0. If I take d mu commuted with d nu, that's i.e. d mu a nu minus d nu a mu, right? It's equal to i.e. f mu nu. And so then the a2, let's just go back up here and take a look at it. A2 has 1/12 times that thing squared. So it's IE squared over 12 F mu nu, and this matrix element log O is then just, there's all these factors, minus I over 4 pi d over 2, m d minus 4, I squared over 12, f mu nu, and there's a gamma of 2 minus d over 2. This is pi of 0 f mu nu. Okay, this is the vacuum polarization function that we had there, calculated dimensionally. But the beauty of what we're doing here is just think about it. Think of how we calculated it before. First we sat there and we derived the Feynman rules. Then we put it in a loop integral. We did Feynman parameterization of the loop integral. We extended that dimensionally, calculated the loop integral, and got this answer. Here, we've done the loop without doing anything. Okay, so this is a real quick way to do this. Gilkey's done all the work for us, and in fact, it's not that hard. You'll see the derivations in my thing there. So there's no need for the loops. Okay. So this is excellent for many tough problems. It's excellent for doing renormalization in fancy theories. It's excellent sometimes for finite pieces. Sometimes it's hard because, as you see, the finite pieces come a little higher up in the expansion. But it's certainly good for many calculations that you have to do. Okay. So let me stop there. I'll let you play with that in the homework. If you have troubles, come by. Okay. Next thing we need to do is Fermion. Okay. So the key thing, when we did bosons, we had the free property. The thing, if we're doing perturbation theory, the most important thing is this functional of the external source. So it's integral d phi e to the I integral d4x L0 plus j phi, and we do that path integral, and we end up with some number e to the minus I over 2 d4x d4y j of x Feynman propagator of x minus y j of y. Okay. And then we use this to develop all the perturbation theory. For fermions, we want to do the same thing. Let me tell you the answer before we sit there and work through a derivation. We're going to want sources. We have two fields. We have psi and psi bar. So we'll have sources that we'll call eta of x, eta bar of x. And we'd like to have an answer that comes out similar. So j of eta, eta bar, obviously z is that, comes out as e to the I integral d4x, d4y, eta bar of x, Feynman propagator of x minus y, eta of y. Okay. Because then if we take functional differentiation, we'll get back to propagator. Okay. There are going to be issues. There's going to be ordering issues, and there's going to be signs that you have to watch out for, and eta and eta bar will have to be anticommuting. Okay, so that's it's going to be unavoidable because the fields that you get after differentiation, well, are going to be anticommuting. Now let's imagine that I have, actually let me give you the alternate form of this here, n integral d psi bar e to the I d4x L0 plus eta bar psi plus eta psi bar. Okay, it's conventional that you, since this is always psi bar psi here, it's eta bar psi. And I should actually have written that in the reverse order. Let's go back. Psi bar eta. Okay, and so the fact that psi and psi bar anti-commute, and you get psi and psi bar by functional differentiation, is going to require eta and eta bar to anti-commute also. So let's go through that before we, again, this is the preview to the formal development. Anyone have questions about that stage? No. So here, anti-commuting sources. Okay. So let's just assume that they are anticommuting at the moment and just show you how functional differentiation works. If I have the integral d4y, eta bar of y, psi of y. Okay, that's my something that sits in some exponent somewhere. And I take the variation with respect to eta bar of x. Okay. That's going to be exactly what I expect, since the eta bar and the eta are sitting right next to each other, that you differentiate it. That just becomes psi of x. If I take instead integral d4y psi bar of y, eta of y, and I take delta eta of x, so functional differentiation of that beastie. Now, if these guys are anticommuting, everything anticommutes. To bring this guy past psi pulls out a minus sign. So this is going to be defined as minus psi bar of x, since it has to anticommute. Okay. Okay, so then when we have this, then we have the e to the I integral d4y eta bar psi plus psi bar eta sitting there in the source terms. And I take delta eta bar of x, that's equal to I psi of x, e to the I stuff again, and delta eta bar of x of the same thing is minus I psi bar of x. So this tells us that if I want to bring down the propagator, this is going to work out right. Okay, let me go back up here just momentarily. I have this here. If I differentiate first with respect to eta, and then eta bar, and then respect to eta, I'm going to get the propagator. And that tells me that let's see, what is it that I want? I want g2 of x prime is 1 over z of 0. I want plus I minus I delta, let's I'm trying to get this ordering right. Eta bar of x delta eta of y of z okay, so this brings down this one brings down a psi bar, and this brings down a psi. Good, so I've got them in the right order. This is then 0 time ordered psi of x. I've got my notations. Let's call this x prime. So that's turned into x prime. Psi of x, psi bar of x prime. So that's that from the differentiation of this form. And if I differentiate this form, it's supposed to come out to be ISF of x minus x prime, but it looks like I'm missing a sign. So I'm going to have to assume it's a minus sign right there. Excuse me. My notes seem to be off. Okay, we're about to develop it anyhow. Okay, so there's our goal. This is, if you then have this form, you can develop perturbation theory the same old way. Actually, let's write that out just so that you see it. Perturbation theory. If you have a full z of eta prime, which is the integral d psi bar e to the I integral d4x some L0 plus L interaction of psi and psi bar plus eta bar psi plus psi bar eta. We do this trick where we replace psi and psi bar here by d by d etas, so it becomes the integral I integral d4y, the interaction Lagrangian of psi is just minus I d by d eta, so minus I partial respect to eta bar, and psi bar is plus I because of that term, partial with respect to eta. Okay, then times z0 of eta and eta bar. Okay, so you pull this out. The only trick here is those signs, and for bosons it was always minus I for everything. Here there's minus I or plus I depending on what it is. And then you develop, you expand and read off the Feynman rules. Okay.
Excuse me.
Yeah.
I don't know why you put negative one page after you take constant derivative of the anticommuting.
I'm sorry. Why do I get the minus sign?
Yeah.
Okay. So all these beasts, the Fermion fields and the sources, are all going to anticommute. So in this case here, this eta, as it goes through psi bar, to sit next to this eta here, picks up a minus sign. Okay, so as you bring this past, it's a minus sign there, and so that gives you that minus sign. Because, right, okay? Yes. Okay, so let's get it right. This with psi there is with respect to eta bar, so let's be clear on that. That's eta bar, and this one here is eta. Okay, so that's as I came back, I was also wondering whether this is the continuation of my delta or whether it's a bar. Okay, I hide behind my sloppy handwriting. Okay, it was really right. Okay, so that's the beast that we want to do. Any questions before we do a little formalism? So the formalism has to do with Grassmann numbers. Okay, so these are numbers that anti-commute. So if you have a number alpha, if it's an anti-commuting number, alpha squared is 0. If you have two numbers alpha and beta, they also anti-commute. So alpha squared is 0, etc. So amazingly, you can build up a consistent set of calculus using such numbers, and we're just going to go through quickly the properties of it. If I have some function of an anti-commuting number, it can only have two terms. If I imagine Taylor expanding it, f1 of alpha, any alpha squared piece vanishes. If I have a function of two such numbers, that's g0 plus g1 alpha plus g2 beta, g3 alpha beta, and it stops there. So that's the algebra. Differentiation is treated as before. D by d alpha of alpha is 1. D alpha of beta is 0, etc. So this implies that d by d alpha of f of alpha is f1. F1 is just a normal number. D by d alpha of g alpha beta is going to be g1 plus g3 beta, but d by d beta of g of alpha beta is g2, which is the obvious one, minus g3 alpha. Okay, and this again, this is the same thing we just talked about there before. To differentiate this term with respect to beta, I have to take the differential operator past the alpha, it picks up a minus sign, and so you get a minus sign right there. And d squared of anything is always 0. Okay, the tougher one to explain is integration. Okay, and this is it is a bit odd, but it turns out that to find the calculus right, the most important property is the translation property. Okay, so if I have some integral d alpha of f of alpha, it's the integral d alpha of f of alpha plus beta. Okay, that turns out to be, in setting up this formalism, the important property. It's sort of like the usual one. If you shift the variables and you're integrating over all the integrating over all of dx, and you shift it by an arbitrary amount, the integral should be consistent, and it comes from things like just that something like d, the derivative with respect to of this respect to alpha is the same in the two cases. So that's where it comes from. But when you implement it in this case, it looks a little funny. So if we have the f of alpha plus beta is f0 plus f1 alpha plus f1 beta, then the integral d alpha f0 plus f1 alpha has to be the integral d alpha f0 plus f1 alpha plus f1 beta okay. So the first stuff is identical, but this last one then requires that the integral d alpha f1 beta has to equal 0. And since beta is completely independent, is arbitrary, this implies that the integral d alpha is 0. Okay, there's the oddity that comes out of this. Okay, that when we're defining the integration of 1 is 0, but the integration d alpha of alpha is not. It can be a number. It can be any. Actually, it can be defined to be any number. You can tell it's a real number. It's not a Grassmann variable itself, because there's two of them here. So if I take beta, I commute it through twice. I pick up the same sign. So it's a number, and it's just defined to be 1. Okay, so that this integral here, integral d alpha of f of alpha is f1. Okay, there's the oddity. Okay, if we have more variables. Okay, let's take alpha 1 and alpha 1 bar just to, because I'm going to start generalizing this. And the integral I'd like to do is one that we're interested in doing here. It's going to be the integral d alpha 1 bar d alpha 1 e to the minus alpha 1 bar m alpha 1. Okay, m is just a number here. It's going to turn into a matrix when I start getting more and more variables in it. Okay, but you can see that this works out is then, so the integration the exponent goes like e to the 1 minus alpha 1 bar m alpha 1. Okay, because it stops at that because there's no squared terms. And the integration that we did before just tells us that the integral turns out to be minus 1. Together, if you pull this one through there, integrate that, gives you 1. Then I'm left with that next to that. So this is just m. Okay. Then yet more. Okay, let's take alpha 1, alpha 2, dot, 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 arbitrary number there, alpha 1 bar, alpha 2 bar, dot, dot, dot. So I then have in the form d alpha 1, d alpha, let's put it in n bar down to d alpha 1 bar, d alpha n down to d alpha 1, e to the minus I, no, there's no I, e to the minus alpha bar I mij alpha j. Let's imagine doing that. The way you do that is you diagonalize, and then you use the above one. So it becomes then a series of diagonal ones. It becomes then the product overall I equals 1 to n of mi, which are the eigenvalues. Okay. So I diagonalize that. I have then a series of integrals all look exactly the same. Each of them gives me the eigenvalue. And you don't have to do it. I mean, you can actually work it out, you know, with a 2 by 2 or a 3 by 3, but this is the way to prove the general one. And this is then the determinant of the matrix M. Okay. So if we then generalize the fields, so alpha I turns into some psi of x, alpha bar I turns into psi bar of x, okay. Then z is going to be the integral d psi bar, d psi, e to the I integral d for x, psi bar o psi, which is going to then turn into the determinant of O. Okay, so just like for bosons, remember, a single boson gave us the determinant of O to the minus a half. Here, fermions give you determinant of O to the first power linearly, not minus power. Okay? Then the next thing I have to do is the source one. But anyone want to ask anything about this stage? We're okay here? All right. So now if we add sources, I'm going to want z of eta and eta bar to be the integral d psi bar d psi e to the I integral d4x. Well, let's put in what the operator is. It's psi bar I d slash minus m. That's psi plus eta bar psi plus psi bar eta. Okay. And the technique, of course, is to complete the square. We want psi prime of x is psi of x plus integral d4y, Feynman propagator of x minus y, eta of y, psi bar prime of x is psi bar of x plus integral d4y, eta bar of y, sf x minus y. And then since I'm going to use I del slash minus m, sf is delta 4 of x minus y. Then we have integral d4x psi bar prime id slash minus m psi prime is the integral d4x psi bar id slash minus m psi plus eta bar psi plus psi bar eta from the cross terms, and then plus integral d4x d4y eta bar of x sf of x minus y eta of y. Okay, so then if we use integral d psi is integral d psi prime. Okay. We end up with then z of eta and eta bar is z of 0 and 0. Okay, so we start with this. This is, this piece here is that minus this piece, and the psi prime integration is just a constant, and we end up with either minus I integral d4x d4y eta bar of x sf x minus y eta of y, which is what we wanted. And let's just go back and see if I got the sign right now. Yes, very good. That was the sign that I added because it didn't work out right. So now we know the functional differentiation works out right. Okay, good. So any questions on that? Okay, if not, I'm going to leave these path integrals behind. I want to make one brief comment on spin and statistics, and then go on to some Dirac algebra stuff. Let's get another couple pages up here. Yeah, well, hopefully we'll be there by the time I get there. All right, so spin statistics theorem. Okay, so the theorem states that what we've been using all along, that integer spin has to use commutators and ends up then with Bose-Einstein statistics. The half integral spin has to use anticommutators and ends up with Fermi-Dirac statistics. Okay, so that's, it just says what we always end up using. So the proof originally is by Pauli. The standard reference is a book by Streeter and Whiteman. It's a very mathematical physics book. The best pedagogic one that I know about is Weinberg's Quantum Field Theory, book number 1. So if you want to read it, try it there. I mean, I have not paid that much attention to it, but I do want to say what the ingredients are. Because these things, of course, could go wrong. One is Lorentz invariance. So Lorentz invariance is, of course, something that we expect in nature, but it's not sacrosanct. You can have theories that are not Lorentz invariance, so therefore you could violate this theorem. Positive energies positive norms so the norm being greater than 0 is not something I have an idea on how to get rid of. Positive energies is a bit of a funny one, since energy is generally measured from an arbitrary point. But I think it makes sense that you can always define an energy that's always positive. So that doesn't seem to be too big. And causality. Okay, so causality also is not something you're very much willing to give up. So of these, the weakest is probably Lorentz invariance. And there actually is a counterexample. The counterexample is in 2D. In 2D, of course, you know, this is a theorem that's been proven in 4 dimensions. That's where Lorentz invariance comes in. In 2D, it's not true anymore. In 2D, there can be anyons, which are anything between a boson and a fermion. So if you have psi 1, psi 2, that can equal e to the I theta, psi 2, psi 1, for any theta. You can have any statistics at all. And so these guys are not just a curiosity, they actually play a role in the fractional quantum Hall effect, the description of the fractional quantum Hall effect. So, I don't know a good field theory description of, an easy field theory description of these guys, but, okay, so that's spin and statistics. Any questions? Okay. So I want to do a few things on Dirac algebra because this is something that we sloughed over in the first course, and we have to get up to speed on that to do gauge theories. So recall for fermions, if we have this vertex here, it's minus I e gamma mu. If we have a propagator, it's I over p slash minus m, which really is I p slash plus m over p squared minus m squared. Okay, there's a plus I epsilon. implied. So we need to do a few things here. I'm going to use the standard basis in everything I do. So gamma 0 is going to be 1, 0, 0, 1. Those are 2 by 2 matrices. Gamma I is equal to 0 sigma I minus sigma I 0. And I'll use the convention that gamma 5 is minus I gamma 0, gamma 1, gamma 2, gamma 3, which converts it into 0, minus 1, 0. Many other people use the convention where this is plus 1, but then you have a lot of minus signs in your formulas, whereas this one, if you use this one, you end up for much of the weak interactions without extraneous minus signs. You don't have to worry about it. There are, for the basis of states, okay, these are 4 by 4 matrices. And so we can define 16 matrices as a basis. So these matrices, the typical choices are the matrix 1, the matrix gamma 5, matrix gamma mu, gamma 5, and sigma mu nu, which is defined to be I over 2 gamma mu gamma nu. Okay, so let's just quickly do the counting. The numbers of these, clearly there's 1 plus 1, 4 plus 4. So up to 10 there. The sigma mu nu's, it's anti-symmetric, so there's 3 of them that are of the form 0i. Anti-symmetric and 0i is fine. And in the ij case, there's 1, 2, 1, 3, and 2, 3, and those are the only anti-symmetric ones you can get. So this equals 6. So this does total to 16. So any Dirac matrix that you have can be broken down into products of these. The one that you might, if you look at this pattern, 1 gamma 5, gamma mu gamma 5, you might ask, why not sigma mu nu gamma 5? Okay. Sigma mu nu gamma 5 turns out not to be independent. It's minus I epsilon mu nu alpha beta sigma alpha beta. So if I were to add this to the list, it'd be redundant, and I don't need it. Okay. So there's, let's call that thing number 1. So we need to know that. Thing number 2 in this is that the order counts. Okay. So one of the most common mistakes that novices make when they're writing out Feynman rules with fermions is to stick the gamma matrices in the wrong places. So let's do 2 examples. I'm going to do one, and then I'm going to have you guys do one. Okay, so let's do Compton scattering. Compton scattering has the following form, following 2 diagrams. So let's call this K. K prime, P, P prime. This is then P plus K. And the initial state is sitting off to your left. The final state's on your right, so it's going out, goes out there. And the same over here. K, K prime, P prime, P. The is P minus K prime is the denominator there. Okay, so let's write out these. So A, B, M, A. Okay, unfortunately our drawing and our writing go reverse directions. So when you write, you start off to this side over here as the initial state, and you end up on the left as the final state. The picture goes the reverse way. So on the Fermion part here, we're going to have a U of P as my initial state. That's an initial state. Comes in, at the first vertex that I just tapped, I hit a minus I E gamma mu. So let's explicitly say this guy is mu. So it's mu here. K will be associated with nu, and we'll have an epsilon mu of K associated with that. Okay. Then I hit the propagator. The propagator has to sit there. It's I over P slash plus K slash minus M. Then as I follow along the Fermion path, I hit the next vertex, minus I E gamma nu. That's hooked up to epsilon nu K prime star because it's the final, and U bar of P prime. All right, MB. So what's the matrix element here? Anyone want to read it off for me? Okay. We start, the initial state is still U of P. And what happens next? I think that's the only real trick we need to do. Is the next thing that happens as we're coming in this propagator is we hit the vertex associated with the outgoing one. So it doesn't look like this, it's that guy, right? So it's minus I E gamma nu. Again, we have epsilon star nu of K prime, that's invariant. Likewise, this will still be epsilon K. The propagator is probably obvious to everybody. I over P slash minus K slash minus M. Or we could have used this as P prime plus, okay, actually I have a mistake there. It's P slash minus K prime slash, or P prime plus K minus M. Could use either. And then finally this is minus I E gamma mu. Okay, U bar P prime. Okay, so order counts. All right. Let me just take this and do one sample calculation since I have it here. I'll do gauge invariance. And doing gauge invariance is often a good check to make sure that you have the matrix element written in the right order, because otherwise it's not going to work out. So what we have here, this Compton amplitude is epsilon star nu of k, epsilon mu, no, that was k prime, the first one's k, some m mu nu. Okay, which had the two forms which you can read out there. Since a mu goes to a mu plus d mu lambda is gauge invariance, okay, if I Fourier transform both sides of that, that says that epsilon mu, okay, going to epsilon mu of k plus some constant times k mu is also gauge invariance. So this then requires k mu m mu nu equals 0 and k prime nu m mu nu equals 0. So it's specific. K goes onto the index at the epsilon for its polarization gets dotted into, and k prime goes to the other index. Okay. So let's check this. K mu m mu nu. Okay. There's a minus I e squared and I that gets pulled out. Both terms have a u bar p prime. Let's give myself the maximum amount of room and put the u of p over here. And then if we just go up here, one more, there we go. If we go there, the sum of these two terms is m mu nu. I'm dotting k mu into it, so the first one, the k, gets dotted into this. The second one goes into that. Let's just do this for good practice. So the first one is gamma nu 1 over p slash plus k slash minus m, and then k mu dotted into gamma mu is k slash. The other one has the k slash over here, and it's 1 over p prime slash minus k slash minus m is the other propagator, and the gamma nu sits over there, and I didn't need all that space. Okay. Okay. But then I'm going to use the following. If I have, that guy right there is k slash sitting next to a u bar, so I can write that as k slash u, u of p is p slash plus k slash minus m u of p, because p slash minus m on u of p is 0. Okay, and you see what I'm about to do. This term equals that is going to exactly cancel the propagator. So on the other side, I have u bar of p prime, k slash, that's going to be written as u bar of p prime I write it as minus p slash prime minus k slash minus m by the same old trick. Okay. So this yields then K mu M mu nu is, well, there's these constants out in front, U bar, and I guess I can just, at this stage, save the writing. Case that turns out to cancel that. This guy turns out to cancel that. It becomes gamma nu minus gamma nu U P equals 0, and I get gauge invariance. Okay, let me stop at this place. We have a few more things to do on fermions, and then I want to do some practical group theory after that. Okay. And then we're done all our review and extension section, and we go on to gauge theories. Okay. Anybody? No.